So we're looking at question 6 now. It says let x, y and z be three positive primes. So positive and prime. The progression or progressions in which root x, root y and root z can be three terms is. So we have to check all these and we have to find out which of these progressions can have these terms root x, root y, root z, where x, y and z are three positive primes.
Exactly. So here basically we are not really given anything. Okay.
Yeah.
So we'll just start with considering the validity of each of the options.
Right.
And in such cases, we generally start with arithmetic progression.
Okay.
Because the formulas of that are the easiest to apply.
Right.
Okay. So we assume that these root x, root y and root z, okay, these are prime numbers, we know, x, y and z.
Right.
So we assume that these three are in AP. So and obviously their roots, root x, root y and root z, these are not rational numbers, we know. Okay. So we assume that these three are in AP.
Right.
That way we see that if these are in AP, then root y should be equal to root x plus n minus 1 into d,
Right.
and root z should be equal to root z
Right.
into plus m minus 1 into d.
Correct.
These where m is equal to the number of terms after which the z comes in, where z is the mth term in the AP and y being the nth term in the
Correct.
AP. Okay, which we took these n and m because we are given that they are not necessarily consecutive.
Yep.
So we consider that they are in AP. Now, if that way we get root y minus root x by root z minus root x.
Okay.
That will be equal to n minus 1 by m minus 1.
Right.
If you see.
Right.
Because, okay, so that is...
That we guessed just from manipulation.
This
of
was
those
into
two
d.
relations.
Okay. So basically, yeah, d got cancelled.
Right.
So we see that this is n minus 1 by m minus 1.
Correct.
Okay. So this is a rational number.
Right.
Okay.
Okay.
This should be a rational number. But we are given that x, y and z are prime numbers.
Okay. And root of prime cannot be rational.
Exactly. Since those are prime numbers, so this should obviously be irrational.
Irrational. Correct.
Okay. This is irrational.
So that's a contradiction. we
But
have.
this is obviously rational.
Okay.
Because n and m are natural numbers.
Right.
So we see that we have arrived at a contradiction.
Right.
Okay. So hence these cannot be in AP.
Correct.
Okay. So we come to the conclusion that the condition AP, this does not hold.
Okay.
Similarly, if we assume them to be in GP or HP,
Right.
okay, we'll again by applying the conditions of the common ratio in geometric progression and similarly in harmonic progression,
Okay.
we'll come to the conclusion that these cannot be in GP or HP also. Okay, so answer here comes to be none of these.
Okay.
So basically what you need to learn in this question is that there do come questions in which the answer is none of these, and generally we get confused and we do try to manipulate ourselves to get into one of these options.
Okay.
But you just need to be confident on your concepts and the concept of rationality here, for example.
Right.
You just need to put in your mind and apply it.
Okay. So, walking through it, we already saw why, for example, we saw a contradiction when we assumed them to be in AP. Similarly, if we assume them to be in GP, we'd get another contradiction because those two are primes.
Exactly. This is another
For example,
case.
if we thought there was three consecutive terms, then y would have to be equal to root x z.
Exactly. And this is another case in which again we start by considering the options to be correct.
Right.
This we have done in one question before also, okay, where we actually check the validity of the option.
Okay.
So this is another way to solve at least half of the questions can also be solved this way.
Okay, so I see that since we arrived at a rational irrational contradiction in AP, we would expect a similar contradiction in HP.
Exactly, because again the condition of the nth term, we find the nth term again similarly
Again, so
in
that
GP.
will hold on. But
Exactly.
in GP, how does it say? Let's say root x, root
In
y,
GP,
and root z.
the term will obviously, we know that the nth term is a r ki power n minus 1. Okay.
Right.
So again there, that way we assume the common ratio to be r. Okay. So that way, if we say, for example, so root y will be root x into r ki power n minus 1.
Right.
Similarly, we could find root y.
Right.
Root z.
Okay.
That will be root z is equal to root x into r ki power m minus 1.
Correct.
Again, so basically manipulating this also, we'll again reach a fraction,
Okay.
in terms
fact, you
of
can
n
just
minus 1
divide
and
it.
m minus 1,
Right.
which should be rational, but our fraction will come to be rational because these are prime numbers.
Okay, so we see that no matter what progression we assume these numbers to be in, we always arrive at a contradiction which involves rationality.
We'll be at a contradiction, hence these can't be in any of the progressions.
So the answer is none of these.
Exactly.
Okay, very good question. And so now that is it. We'll move on to the 7th one. So problem 7 says that if our x, y, z are all greater than 1 and are all in GP, then we have to find what progression the following terms can be in, and the terms are 1 by 1 plus log x, 1 by 1 plus log y, and 1 by 1 plus log z. All these logarithms are natural, and so obviously we would remember from theory that whenever we have x, y, and z are GP, there is always some logarithmic relation there.
Y square is equal to xz.
Okay,
Again
so we are going back to...
Yeah, again we see in this question we are given nothing but the fact that these three terms are in GP.
Okay.
So we just apply the basic condition.
Right.
That is y square is equal to xz.
Correct.
This is what we are given.
Right.
Now, obviously, you can see that we are to find the answer in terms of log. Okay. So we just take the log on both sides. Okay. Log on both sides.
Okay.
And we get 2 ln y should be equal to ln x plus ln z.
Okay.
Okay. So adding 1 to both sides.
Right.
Adding 2 to both sides, I'm sorry. So we get 2 into 1 plus ln y
Right.
should be equal to 1 plus ln x
Plus 1 plus ln z.
plus. The catch is that how did I get it? That we have to add 2. The thing is we get this from the question.
Right.
We see the term that we are supposed to get the answer in the form of.
Okay.
Okay. Now we see that we have arrived this condition.
Right.
Which we see that this is a condition of an arithmetic progression.
Yep.
This being the middle term, this is the first and this is the last one.
Okay.
Okay. So we say that 1 by 1 plus ln x. 1 plus ln x, 1 plus ln y, and 1 plus ln z.
Are
These
in
three will be in AP. Exactly.
Okay. So obviously we are going towards HP.
Exactly. And since in the question we have their inverse, so their inverse will obviously be in a harmonic progression.
Exactly.
Because the three terms are in arithmetic progression.
Right.
So here we see that from the term we came to ln thing. Okay. So basically handling the concept of log is it's nothing there. Log wasn't really there. We just took the log on both sides.
Right. So as we can see, whenever three terms are in GP and you see logarithmic, there's usually a transition from GP to AP, and when you see an inverse, there's usually a transition from
AP to harmonic progression.
Exactly. So after a point, you don't even have to stop and think about what this might be. It will just be built in.
It's just practice. After that, it comes naturally.
Exactly. So that was problem 7, and we'll see problem 8 now. So problem 8 says we have to find the sum to n terms of the following series: 4 by 1 into 2 into 3 plus 5 by 2 into 3 into 4 plus 6 by 3 into 4 into 5, and so on. So yeah, there is an obvious pattern. It says n plus 3 by n into n plus 1 into n plus 2.
Exactly. So here we first define our rth term as being r plus 3 into r plus 1 into r plus 2.
Correct.
Here, as we see, we could just separate it here. Okay.
Okay.
So that will be r by r into r plus 1 into r plus 2 plus 3 by r into r plus 1 into r plus 2.
Right.
This gets cancelled.
Okay.
Okay. So here we see we could just separate this term. Okay. So it becomes 1 by r plus 1 minus 1 by r plus 2.
Right.
Okay. And here it becomes 3 by 2. We just take 3 common and then multiply and divide the term by 2.
Yeah.
Okay.
Because we have to put a difference inside.
Exactly.
Right.
So here we put it as 1 by r into r plus 1 minus 1 by r plus 1 into r plus 2.
Correct.
Okay.
Right.
So here we see after this. Now this is our rth term.
Right.
But we need to find the sum. Okay.
Right.
So there's this technique of converting the nth term into the form in the form of a sum. Okay. Once we get the term in this form such that the fractions, okay, these terms are consecutive as we can see.
Right.
Here again, these are consecutive.
Right.
So if our terms are in this form, okay, we could convert this nth term thing to the sum.
Right.
How? We just put 1 to the term-wise smaller number. I'll just tell you how.
Okay.
Term-wise smaller number
Right.
and n to the bigger one.
Correct.
For example, here to this we put 1, To this we put
This
n.
happens because when we sum the series, there will be diagonal cancellation in consecutive
Exactly.
rows, and
We could
only the
solve-
first and the right.
Exactly, we could just we could solve it by just putting values r is equal to 1, 2 and 3 and just do the summation. All the terms will get cancelled.
Okay.
So basically
only
this
one
is
and n will be
this is the
remaining.
shortcut to just save time
Right.
for converting the nth term to the sum of n terms.
Brilliant.
So again we see this is the smaller term, so here 1 and here n.
Right.
Okay, so that way we get this is 1 by 2 minus 1 by n plus 2. Okay,
Right.
and plus 3 by 2 into, that is 1 by 2 again, and 1 by n plus 1 into n plus 2.
Correct.
Okay, so this will be our answer.
Right.
So basically what we see here, we could solve it to get the answer further.
Yeah.
The main catch in this question was, see where I have written below, if possible we express the RS term as a difference of two terms, as TR is equal to f of r minus f of r plus 1 into r minus 1.
Right.
So we see that r minus 1 and r, these are again consecutive terms.
Correct.
And r plus 1 and r, again these are consecutive terms.
Right.
And don't forget that this condition of, like, you know, this putting this 1 to the smaller term and n to the bigger one, we can do this only if the terms are consecutive.
Right.
And this we do whenever we see a question, a big series in the form of fraction. We try to break it as much as we can, and
Right.
then we simply apply this trick and the question gets solved within no time.
Exactly. So that we do because there is no other way to work with fractions.
Exactly, it's a series till infinite, okay, and it's a complicated series, so no direct formula of AP, GP or HP is being applicable
Okay.
here.
And in case any of you are wondering whether this really works or not, it works because if you build on consecutive rows of these and then
Yeah,
add
you could
all of
you
them,
could just on putting a see if we put a summation here this side, what we have to do, like this should be like r is equal to 1, then
for
r is equal to 2.
example, r plus 2 would be r plus 1 for the next row, and
Exactly.
like that they'll get cancelled
Exactly.
diagonally. So
And
you would have the leftmost.
Only the first and last term will
Exactly.
be remaining.
Right. So that is how this thing works, and you would have seen this in theory, and we just show you how to use it to solve JEE problems. So there was problem 8, and we'll move on to the next one now. Okay, so we see problem 9 now. It asks us to evaluate the expression 1 plus 1 plus b into r plus 1 plus b square into r square and so on to infinite terms, and we are given the condition that mod of br is less than 1. So we can see that it's not a common progression, so how do we go about it?
Exactly, we see in this question that no pattern is defined. Okay, neither is it is not an AP, not a GP, nothing, and the series is still infinity.
Yeah.
So we'll just start with it and we'll see what we can do. So here we see that S is given 1 plus b into r plus 1 plus b square into r square and
Right.
so on. Okay, now we just multiply this whole thing.
Hmm.
We define as our number 1. We
Okay.
just multiply it by r.
Okay.
And now we see that this becomes r. We just shift the terms. We just shift the expression one term to the right.
Exactly. So this
Okay.
is how in fact we get
Exactly,
summation
this is a new
formulas
technique.
for
This
lot
is
of
exactly
things.
a new technique. Just another way of solving the question.
Right.
We'll just
in fact, this is how we arrive at the expression for sum of GP and all those series.
exactly,
Right?
exactly. See here. Now we say that like let u1, u2 and u3 be a sequence, okay, such that their difference here we can see the इनका जो difference है, okay, that is in GP, okay, 1 plus b and 1 plus b square,
Right.
okay, उनका difference is like b square.
Right.
So again, अगर ऐसा होता है and in the series you can't really find a good pattern.
Right.
We just define our series and then we just put it again, multiplying by some term, some
Okay.
required term, and just shift it one term to the right.
Right.
And then we just subtract the two.
Okay.
And by this, what we actually get is that the nth term we get of the series, the nth term we get.
Right.
Okay, so that way, after finding the nth term, the series is basically we get that if it is in AP or in GP, and then we can just solve the series further. Basically, it just simplifies it.
Right.
We just look at the question and we'll see how it makes our work easier.
Correct.
Okay, so we were just multiplying it by r. Okay, so it becomes plus 1 plus b into r square
Right.
and so on.
Correct.
This is number 2. We just subtract 2 from 1.
Yeah.
Okay, so basically 2 from 1 we are subtracting,
Right.
so it becomes 1 minus r into s. That becomes what? 1.
Right.
plus br, that is b1 plus bn minus 1. Okay, 1
Right.
plus br
And I see b square
plus
r
b square r square
Oh,
and
okay.
so on.
So we already
plus
know that this
b
is a
cube
GP with
r
common
cube.
ratio BR.
Exactly.
Infinite, and
So-
we are already told mod of BR is 1, so we can straight away write the sum.
Exactly. Now this is a defined series.
Right.
Okay, we can find this is a GP. This GP till infinity.
Right.
And we are given that mod of BR, that is a common ratio here, that is less than 1.
Right.
And we also have a formula for that.
Yeah.
That was a by 1 minus r.
Correct.
Okay.
So this is straight away B.
Exactly. Here our first term is 1 and obviously the common ratio is BR.
Okay.
So the sum for this will be 1 by 1 minus BR,
And then we divide by 1 minus R.
1 minus R.
Correct.
So basically this is the answer to our question. So
Right.
this concept is an important concept, that whenever the series is not particularly defined, we just write the series and then we write it again, shifting one term to the right.
Right.
And we just subtract them, and then we surely get some defined progression that we can solve easily.
Correct. So that was problem 8. Problem 9 in fact. So you saw how this technique of writing a summation and then multiplying
this
it
is
with
problem
R.
8. I'm sorry. This is problem 8.
Now we'll have to do it again. So problem 10 says if summation k equals 1 to n of summation m equals 1 to k m square is equal to a x raised to 4 a n raised to 4 plus b n cube plus c n square plus d n plus e. So basically we have a double summation which we have expressed as a polynomial in terms of n, and we have to check whether any of these options are correct or whether none of them are correct. Actually, it's not a multiple answers question, so one of them have to be correct, but anyway, we'll see what happens.
Exactly. In this polynomial, they have just introduced many variables which
Right.
are not really of our use. Okay.
Okay.
We'll just simply start with solving the question that is given. Okay.
Right.
So this is sigma m square,
Okay.
and we know that sigma m square is clearly k into k plus 1
Into 2k plus 1 by 6.
2k plus 1 by 6. True.
Correct.
Okay. For k is equal to 1 say n.
Right.
Okay, sigma here. Now this seems to be a difficult thing. We don't really have to do much. We just have to open the bracket. Okay,
And then since the highest degree is cube, so we can actually sum all of them.
exactly, we know the formula for summation of all of these.
Okay.
So this will be k is equal to 1 to n,
Right.
2k cube plus 3k square plus k. On solving we get this.
Okay.
Okay, so basically we could just break it now.
Right.
Okay, and for this summation for this and summation for this, we know the formulas for all.
Right.
Okay, so on solving we simply get it 1 by 3 into n plus 1 by 2 whole square, that is the formula for summation of n cube,
Right.
plus half into n plus 1 into 2n plus 1
By 6.
by 6
Right.
plus 1 by 6 into n plus 1 by 2, that is sigma n. Okay.
Okay.
So here again we see that we don't need to solve this entire thing. Okay, we just need to check the coefficients of the various
Correct.
degrees of n, and by that we see that a, that is the coefficient of n ki power 4.
Right.
That will be 1 by 3 into 1 by 4.
Okay.
That is 1 by 12.
Correct.
And that is the A option, I guess.
Right.
So, and as one option is correct, we don't really go to the other options because
Exactly.
one option
But if we
correct.
had to, then this is how we would do it.
Exactly. Even
Right.
if it was multiple choice thing, we didn't have to like really solve the entire thing. We
Correct.
could just take the coefficients.
In fact, a very intelligent solution to this problem. We had a double summation and we had it expressed as a polynomial. The first instinct some people might have is to investigate what A and B and C might be from the question itself. But this is much better that you can just sum the entire thing and get a polynomial. And since the highest degree is 3, we can use our knowledge of memorized formula.
The formulas that I gave in the beginning.
Exactly. So those are standard formulas which everybody knows, so we just use them, and then finally when we are down to this expression here, we compare the polynomial and we get degree values of A, B and C and whatever else we want. So
Exactly.
that was problem 10, and we'll move on to the next one shortly.